Hi everybody, Cal here with section 5.2, the characteristic equation. So, we talked in 5.1 about how to find eigenvectors, a basis for an eigenspace for a given eigenvalue. We talked about how to find eigenvalues in the very special case where we had a triangular matrix. But we didn't learn how to find eigenvalues in general, and we had the dire warning that you could not just row reduce to a triangular form. That does not work. So we need a method that we can get at our eigenvalues in general. Example 1 is a motivating example, and it's going to kind of run through the logic of how this is going to work. And we'll go over this in class as well, but that's going to kind of motivate how this is going to work. The bottom of the page and onto the next page, the book reintroduces determinants or refreshes you on determinants. And in particular, it reminds you that a matrix is invertible if and only if its determinant is not 0. Now, the gist of this discussion is we have properties of determinants, which you've seen before. So that's fine. So the gist of this discussion is that lambda is going to be an eigenvalue of A exactly when there are non-trivial solutions to the equation A minus lambda I times x equals 0. In other words, lambda is an eigenvalue of A exactly when A minus lambda I is not invertible, or in other words, lambda is an eigenvalue of A exactly when the determinant of A minus lambda I is 0. This equation is really special, and so it has a name. It's called the characteristic equation of A. This thing, determinant of A minus lambda I, is called the characteristic polynomial of A, which is discussed down here. In order to find the characteristic equation of a matrix, look at an example 3. You take A minus lambda I, and you take the determinant. My recommendation is that you do this via cofactor expansion. Do not try to do row operations, and in particular, you may not do row reduction to A before you do minus lambda I. That will not work. Hopefully you heard me. That's a pretty important warning. Now, for this particular example, you'll see here that once they factor the characteristic polynomial, they have a couple of factors showing up twice, right? 5 minus lambda has a square by it. And what we say here is that lambda equals 5 has a multiplicity of 2. It shows up twice as a solution to this equation. Okay? And so the multiplicity of lambda as a root of the characteristic polynomial is called the multiplicity of that lambda as an eigenvalue of A. Example 4 kind of lets you play with multiplicities a little bit. So that's basically how to find eigenvalues of a matrix. You find the characteristic polynomial, set it equal to 0, and solve. That, in general, is computationally prohibitive. We will basically only do it for 2x2s, 3x3s, and very simple 4x4s. And if you were ever to actually want to compute eigenvalues for a large matrix, you would use a computer. Now, there is another concept in this section called similarity, and that's going to also be important for us, not for immediately obvious reasons, but I do want you to know what similarity means, how it's defined. And Theorem 4 is true, but actually, Theorem 4 is pretty useful. I would read over the theorem. I would also read over the proof. It's useful enough and simple. It comes with a warning, though. Having the same characteristic polynomial does not imply similarity, but having similarity does imply having the same characteristic polynomial. And this warning at the bottom of the page gets at that difference. You should know this example by heart. I would take the time to work through it and commit it to memory. You can ignore the part about the application to dynamical systems. So that kind of ties up that section.